1 week ago, we have reached this circuit. This circuit comes from the equivalent circuit model. It includes the mechanical model with electrical and electrical. This is the power supply. And this is the output port. And the mechanical system, we have MEMS. We have, this is, say, 1/k. So this is spring. This is the damper. So the damping system can be equivalent to resistor. The mass of mechanical system is equivalent to the inductor of the circuit. And the spring constant K is equivalent to a capacitor with capacitance 1/k. And the interface between the electrical system and mechanical system is a transformer. So this one is a transformer to transform the current into the force. The force is equivalent to the voltage. And this one, the voltage. And we have the current. And the ratio is gamma D and gamma S. We can use LT SPICE to simulate this system because in LT SPICE, we have transformer, we have capacitor, we have power supply. We have all the components we need in LT SPICE. So using equations 3, 4, 7, 9, and 10, and the ideal transformers, then we could model this two port 1, port 2. So port 1, we have voltage, we have current. And port 2, we have voltage and also current. Then today, you will learn how to use LT SPICE to run this circuit. So we have four, we have 1, 2, 3, 4. We have 4 students. They are good at the LT SPICE. Then we will divide each one into 4 teams. Okay, so I will come back in, say, 5 minutes. So after 5 minutes, each one should select. So we have 4 chain. Ahmed, raise your hand. And me. Also, Agan. Okay. So, are you okay with LT SPICE? Okay. So, we need to divide the whole class into 4 teams. Okay. Camera off. Okay. So, we have the equation. For the transformer, we have gamma D is this constant. The relation between FD, this is the voltage drop here, and VD is the voltage from this node to this node. And gamma S, the transformer, we have VS node, and this node, the VS voltage potential. MS is the voltage drop. And IEN, the electromechanical current. Along this circuit, we have IEN. And dxdt is the, dxdt is the current. Voltage is the current. So this is the current of this circuit. And this current times gamma will be the electromechanical current, IEM1. Okay, so this is it will use T-Spice to simulate this circuit. But before we do that, we will continue our lesson. Is the camera on? Yes, we will continue. Then we got this circuit, and this is the circuit equation. Let's look at this one. Q is the charge of this circuit, so dQ dt is the current. So the second differential of Q is di dt. So L di dt is the voltage drop of the inductor, and Ri is the voltage drop of the resistor. Then Q is the charge. Charge times divided by C is the voltage drop of the capacitor. So this is the total voltage drop of this MC, this MLC circuit. Yeah, this LRC circuit. The total voltage drop V of T. And if you take IEM as so this one L di dt. So this is charge, and L di dt, yeah, the same thing. You can just take IEM equal to dQ dt. And this is the mechanical system. For the mechanical system, M x double dot R damping dQ dt. This is the velocity, and this one, you can move this term to the denominator. You get K minus K prime times X. So this is the spring force. So they are equivalent. Okay, any corrections so far? Frank? No? Martin? Good. So using 7, 8, and 12 to derive this one, and also derive this one. 7, 8, 12, we can derive this one, and this one can be written as this one. Using those relations, 7, 8, and 12. 12 here, and equation 7, 8. This is 8, and this is 7. So using those equations, please derive equation 13 and 14. And also the LEQ, REQ, and CEQ. LEQ, REQ, and CEQ. in this circuit. So please derive equation 13 and 14 based on equation 7, 8, and 12. Okay, camera off, please. On. Hugh, could you come here to tell me how did you derive these equations?
Equation 8, we can get Vs out, and from that we will have the FET inside the equation of Vs, and FET will equal this one. So from this one we can get the equation 13. And equation 14, the ds, we can apply this equation I En equal gamma ds over dt, and replace this equation into the equation 13. So can you get the equation 14?
Okay. Master, do you have any problem?
No.
So, Master, did you get the result like this?
No, I just want up to 14.
So, did you get the result?
Only 14.
We have 11 and 12. 11 and 12. So use 11 and 12. Compare with equation 13, 14. And write down equation 15. Okay, please. Okay, camera off, please. In this equation, VT is the voltage cross LRC. The voltage cross LRC, so VT equal to VD minus VS. Do you know that? VT equal to VD minus VS in this equation. So VT equal to VD minus VS. So you need to compare this one with this one. But we have VS, VD here. This V is VD minus VS. Okay? Right, camera off. Not working. Kyler, could you tell me how did you derive equation 15?
I didn't do it.
You didn't do it? Master.
I just consider this these are two equal. I don't know whether it is
then this minus this becomes VT, and this, then we compare the corresponding terms from this equation and this equation.
How did you compare? Because this one is V, and there's no VD.
It's VD minus VS, then it's VST, as you said.
But we have IEM. This is IEM too. So how can you compare? Ethan. Okay, how did you get the result?
就11和14比。
Okay, but we have V, we have IEM, this is IEM too. So how can you compare?
IEM 等于 IEM2。
Why?
I don't know.
Can you turn to previous page? Okay, next. Next. Okay, sorry, previous. Okay, originally we had this equivalent circuit, but we want to simplify this one again. Next page. Next. We want to simplify to this one. See, now there's no transformer. So in this circuit, we assume IEM2 flows through this circuit. So that's why we want to use this as the simple circuit. Previous. For that circuit, VD minus VS is the voltage supply. And this is LEQ, REQ, CEQ. And we have the current. This is the current, but we want to use IEM2 as the equivalent current. That's the reason. Okay. Thank you. So finally, we reach this circuit. Again. Again, could you come here? Oh. See, after several years, the coupling is loose, so they use the tape. So this way, this connection can work. But here, sometimes if I move away, so at the end of this class, please follow this example. Tight. Because this one bending loose. So you tight here this way, we won't have bending here. Also for this one. So the bending causes the connection problem. Okay. Hello. This is the circuit we finally reached. So we have an amplifier because this is the voltage. We have gamma D, gamma S, B, D. So this node and this node, we have this gain of this OP. And CP1 and CP2 are parasitic capacitance due to the bonding, due to the circuit connection. We have parasitic capacitance. Then so this is a sensor or vibrator. We have a big vibration due to applied AC voltage and DC voltage. But for mechanical system, if the vibration is too large, then we won't have linear response. It's not a small, for circuit, we have small signal model, large signal model. For mechanical system, we also have small signal model and large signal model. Large signal model means non-linear response. Small signal model means linear response. So for the mechanical system to be applicable, to be used in small signal situation, we cannot give too much voltage to it. Otherwise, the vibration will become non-linear. If it is non-linear, then the small signal model cannot be used. But because for resonator, we want the vibration to be small. So applied voltage should be small. Everything, circuit and mechanical, should be small vibration, small AC voltage. Okay, so we need to know how much is the voltage we can apply to make the mechanical system still in the electric linear region. Okay, so for mechanical engineer, we derive this equation. This is the critical vibration of the beam. If the beam vibration amplitude reach this value, it will become non-linear, large signal. So this is the maximum vibration we can use. Q is the quality factor. Omega 0 is the, omega n is the natural frequency. And we have another omega 0. Omega 0 equal omega n square root 1 plus 2 epsilon L squared divided by 7h squared. Omega n is the natural frequency, but omega 0 is the resonance frequency. If epsilon is the strain, when we use, say, finite element method to get the natural frequency, means there's no force applied to it. But for our beam, we have, say, internal stress, residual stress. So this is the strain in the beam. If you have strain in the beam, the natural frequency is not omega n anymore. The natural frequency will be omega 0 due to the effect of internal strain. So this is the tensile strain in the beam. And omega n equal to this equation. E is Young's modulus. Rho is the density. L is the beam length. H is the beam cross-sectional dimension. And another relation is if the beam is vibration, we apply the vibration at the resonance frequency. The vibration amplitude equal to F0Q divided by K. Q is the quality factor. F0 is the force we applied. Force divided by spring constant is the static displacement. Force divided by spring constant is the, I repeat again, static displacement. Static displacement times quality factor equal to dynamic amplitude, vibration amplitude. So Q is the link between static and dynamic. Then F0, you can go to equation 1, 2. In the previous equations, we have the F0 equal to epsilon 0. Permittivity, surface area, G is the gap of the capacitor, and VDC, VDC is the DC voltage, and AC is the AC voltage. So we have this equation. Then VAC equal to VD, because V equal to VD minus VS. V equal to VD minus VS. This is small signal model. AC is a small signal. So in that equation 14, 15, V is a small signal. Small signal is AC. So VAC equal to VD minus VS. And using equation 19, 22, this is 22. And this is the criteria. Remember, for the beam to operate in linear small signal model, we require the resonance amplitude less than the critical amplitude. So we have this XC in the previous page. We have XRES here. So using this relation, then we should be able to get the condition. So this is the condition for your electrical power supply. VDC times VAC must be less than this. So the power supply cannot be too large. Otherwise, we won't be able to use small signal model. Please derive this one. Okay. Brainstorming. Kaiser, have you finished? Could you come tell me how did you do this? You got a fever? Are you okay now? Is it COVID-19? Go ahead.
I have compared equation 19 and 24.
How did you compare? Yes.
From equation 19, this part.
Yes.
And 22, this part.
Yes.
So 19 is greater than this one. So from this, I hope put this side here. So we will get VT CBSA. And after some calculation, we will get.
Okay, next page. Okay. All right, thank you. We have K value here. K is the spring constant. So So the relation between this spring constant, you compare these two equations, see epsilon s, epsilon 0 s, g squared, and h. Then, so this k should be equal to rho at w h. And also omega 0 squared. Let me show you how we can get this equation. Because spring constant K has a relation with natural frequency. So omega 0 equals square K over N. So K is the spring constant. N is the total mass of the beam. Total mass of the beam equal to volume multiplied by density. Rho is the density. And WH is the volume. Density times volume equal to mass N. So if you take square of both sides, K over N equal to omega 0 squared. So K equal to rho at WH times omega 0 squared. So that's how we got this solution. Okay, so we have this relation. We are going to use this relation to plot this figure 5. Okay. Figure 5 is a relation between DC voltage and AC voltage. So for any combination of the DC AC value, and this is the boundary. For instance, if Q equal to 10,000, and this is the boundary. Lower than this boundary, any combination of VDC, VAC, we have said is a small signal region. For any combination of VDC, VAC in this region, we reach the large signal area, nonlinear region. So I have this example file. We use the parameter here at 300 W56 H2.1 micrometer, micro. And the capacitor size means S. The area, surface area is 120 times 56 micrometer squared. Then the gap G, we use 0.85 micro. The resonant frequency, we use 400 kHz. Use these parameters. Let's take a look at figure 5.F. Remember, always, when we working with micro device, unit system is very important. So always put your unit system at the beginning. In this case, I use micronewton, micrometer, milligram, millisecond, kHz, volt, picofarad, picocoulomb, nanoampere, gigaohm, mega Henry. So this is the unit system I used for this case. So Q, L, W, H, S, G, Young's modulus, for polysilicon. Rho is the density of silicon, and epsilon is the residual strain. So with no residual strain in this case, E0 is the electrical permittivity. So you can look at the journal paper, omega n equation, omega 0 equation here, because epsilon now is 0. So if epsilon is 0, omega 0 and omega n are the same. So we consider three cases: Q, first element, second element, third element. And we have two loops to plot this curve. For loop 1, we consider three cases: case 1, case 2. So length Q equals 3, I equal to 1, 2, 3. Then J, we count how many points we want to plot. So initial value of J is 1. Then TMP just a parameter, a variable from 0.5 to 4.5. They are V, D, C. If you look at this figure, see, from 0.5 to 4.5, we take this VDC. So TMP means VDC, but we want to plot VDC, so we use this temporary parameter. We set this value into this column. I means case 1, case 2, case 3. J means point 1, because for each computation, J equals J plus 1. So J equal to 1 is the first point. J equal to 2 is the second point. This is the increment. This is the final value, initial value. So the second point is 0.01 when J equal to 2. So I, case 1, 2, 3, J is the curve. This is VDC, and VAC, we use the equation. You derive the equation. So we put the equation here. Remember to use dot multiply. Dot. This is the, okay, I forgot, square, okay. Remember to use dot. If you don't use dot, probably, because this is element, this is not a vector. If you don't use dot, means vector, matrix operation. Matrix operation should give you a matrix. If you don't use matrix, this is a component. This is one element. So element should equal to element. Otherwise, MATLAB will tell you dimension error. Because dimension here, if this is dimension 1, if you use matrix, the dimension is say 3 by 2 or 5 by 6. So matrix cannot be equal to element anyway. Okay, use this one, and this is the parameter, plotting parameter. Then you can plot the result. Okay. So now it's 4 p.m. So next week, I want everyone to participate in this journal paper presentation. So I want to divide the whole class into several small sections of the journal paper. And you will read the journal paper and you will report that paragraph you are in charge to read. So let me find the journal paper. Camera off, please.